Let me disable my Discord. So they're not just chatting all the time. Okay. And I think we're recording now. Okay. So so now I'm going to go into the statement of modules over PIDs. So the fundamental theorem of modules over PIDs. Okay, so that's what today is going to be. Fundamental theorem of modules over PIDs. Okay, so let's state the theorem. So if M is a finitely generated, so let R be a PID. Okay, if M is a finitely generated module over a PID, then M is isomorphic to R mod A1, direct sum R mod A2, direct sum blah, 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 direct sum R mod AM for some M, direct sum R to the R. Okay, so where these elements, so these AIs satisfy that A1 divides A2 divides A3, so on and so forth, and all the way up to AM. Okay, so some terminology. So these things here, so both okay, so both AI and these things R mod AI are called invariant factors. Okay, so we call this factor the invariant factor. The idea is that when you have like this so when you have a linear operation, right, on a vector space, right, what we could do was we could take that linear operator and we could make the vector space into an f of x module, right, where f is the field that we were working with, and the module structure was given by applying a polynomial to a vector by applying the operator, plugging the linear transformation into the polynomial, right? And then when we had a subspace, a vector subspace that was invariant, there we go, thank you. So when we had a vector subspace that was invariant, right, that was one of the invariant factors of the module. Okay, so sometimes people call these, so the terminology isn't consistent. This is what Dummett and Foote call them. But as a warning, some people call these elementary divisors. So there's another thing that we'll call elementary divisors, but it's just for some reason, like Wikipedia calls, I think, these things elementary divisors, right? But we call them invariant factors. But there's another set of numbers too. Okay, so let me give you another way to do this. And these things are unique, right? I should also say these are unique. Okay. And this presentation here is unique. So there's another way to write this.
That'd be unique up to associates, or?
The ideals are unique, yeah, up to associates.
Oh, right.
Yeah, but that means the ideals are unique. Yeah. So there's another way of writing these modules. M, and that is M is isomorphic to R mod P1 to the alpha 1, direct sum R mod P2 to the alpha 2, direct sum blah, 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 direct sum R mod PS to the alpha S, direct sum R to the R. Okay? So this, so here, P1, P2, through PR are primes, not necessarily distinct. And these the P alphas here, Pi alpha I, are called the elementary divisors. Okay, and so you convert between these two using the so yeah. So one thing is that this is what's going to correspond to the Jordan canonical form, this kind of form of it. By the way, to Jordan canonical form. So these things are not necessarily distinct prime dividers. And to convert between the two, so the conversion between this version and this version, the conversion between invariant factors and elementary divisors. So the conversion between invariant factors and elementary divisors goes through the Chinese remainder theorem. The Chinese remainder theorem. Okay, so that is that R mod, if I take a product here, P1 to the alpha 1, P, we need a letter. R, I already used S, T, PT to the alpha T, right? So this thing is isomorphic to R mod P1 to the alpha 1, direct sum R mod PT to the alpha T. Okay, so like these things here, PT, distinct prime factors. So the basic idea is, to get from this piece here, like the thing circled in red, to these pieces here, you essentially break up each one of those little ones according to the Chinese remainder theorem, like this, right? Also, you should be, and to go backwards from here to here, you read the Chinese remainder theorem backwards. Okay, and I'll leave that as something for you to think about how to do this to go the other way. Okay, there'll be a ton of exercises on that. Okay, so that's the statement that we want to prove. All right. Now, okay. So now I need to do so a little bit of stuff on. So now I'm gonna talk about the proof, right? And to do that, I need to say I just want to give you a little bit more about finitely presented modules. Okay, so. Okay. So we need a little excursion here. So so there are some exercises I think I assigned. If not, I'll write them in there. So here's some exercises. First exercise is that if M is a Noetherian R module, and so you should probably be able to get these right away. And N is a submodule of M. Then the quotient is Noetherian. So Noetherian, the two conditions that we think about is that there's no maximal chains of submodule, or there's no infinite increasing chains of submodules, or that every submodule is finitely generated. And those two things are equivalent. And the equivalence goes through this, this maximal element of a set, this like the Zorn's lemma type thing. So there's that third condition that we use to prove that those two things are equivalent. Okay, so if M and N are Noetherian, so these are Noetherian R modules, then so is M direct sum N. Okay, and so you can do this to get arbitrary direct sums. Okay, so these are kind of two things that we can check that I'm going to use. Okay, so so let's do a lemma. Okay, so if R is a Noetherian ring, and M is a finitely generated R module, then M is Noetherian as a module. Okay, so M being a Noetherian ring means that every ideal is finitely generated, or equivalently, there's no infinite increasing sequence of ideals. There's no infinite increasing chain of ideals. All those chains have to terminate. They eventually have to be the same. And here, we're just saying that if you're finitely generated, then we have this condition on all the submodules as well. Okay, so here's the proof using the exercises. Okay, so M being, so this is an important part. Okay, this is kind of an important statement that I want to make. M being finitely generated let's say, by, say, a finite number of elements, M1, M2, Mn, is equivalent to the existence of a surjective map, surjective morphism. Okay, so here from R to the N to M. Okay, and so this map here, okay, so how do we do that? So the map here, so this map sends the elementary basis vector, the basis vector, basis element, I don't know. So it has a basis because it's a free module, right? EI to MI. Okay, So the idea is that you send all the basis elements to the generators. Okay. So just because it's generated does not mean finitely generated does not mean that this looks like a direct sum. So there's plenty of ideals that are, generated by two elements, but does not make it isomorphic to the ring itself. Okay? So since this is surjective, right? So okay, so now we know the ring is so what does this mean? So the ring R to the n is Noetherian. Since it's a finite direct sum or sorry, not the ring, the module. Since it's a finite direct sum of Noetherian modules. So this uses the second part of the exercise, right? And in the map here, this surjective map, okay, we need to give this a name. The surjective map morphism means that M is isomorphic to R to the n modulo the kernel of F. Okay, so this is a quotient by a Noetherian ring, and quotients by a quotient by a Noetherian module, and quotients by Noetherian modules are Noetherian. So quotients by Noetherian modules of Noetherian modules are Noetherian. Good times. All right. So all right. So now we know that finitely generated modules over a Noetherian ring are Noetherian. Okay. So what am I doing all this for? Okay. So what I want to talk to you about is presentations of modules. Okay, that's what the title of this thing was. And what's a presentation of a module? So a presentation of a module is essentially a quotient of a free module. Okay, so it's like I tell you what the generators are, but not only that, I kind of have to tell you what the relations among the generators are. So it's like if I can tell, and this is how it's stored in, this is how modules are stored in computers, say in Macaulay too, right? Is that in order to me to give you a module in a computer, what I need to do is I need to give you the generators, and then I need to give you the relations between the generators, right? It's the same way we talk about groups with generators and relations. Okay, so all right. Okay, so let me just say a little about the presentation. So the presentation here. So what is a presentation? Okay, so note that in the above proof, we can kind of continue this quotient, this process, this surjective map from R to some power process. Okay, and what do I mean by that? So the kernel of that map F, this is a subset of R to the n. Agreed? So this is a submodule. This is a submodule of a Noetherian module. Okay, this implies that the kernel. Let's do it over here. So this implies that the kernel here is finitely generated. Okay, and what does finite generation mean? Finite generation means that this thing here, that there's a surjective map here. Okay, there's a surjective map. This is a surjective map. Okay, so I'm going to do something a little bit. Well, I want to write this A in a different way, right? So A, right? So this A here. So kernel is really a subset of R to the N. You guys agree, right? So the kernel is in this, and so we really have a map. So abusively, let's write A for the map here from R to the M to R to the N. Okay, in the image of this map, is the kernel. Okay, so what we've done is so what I've done is I know that a module is finitely generated. Because the module is finitely generated, you get this map here. So that's from finite generation. Okay, by Noetherianity, right? I get to do another map, so I get another map like this. Okay, and so this thing goes from here to here. So we have this thing. This goes to here, and then this is exact here. So this is surjective, and the kernel of this map, the kernel of this map F, is the image of this map. So this is exact. So the kernel of F is equal to the image of this matrix A. Also the matrix A is an N by M matrix over R. Okay, and so any sequence like this, so a sequence like this, where this is this, let me give you a definition. So a presentation, a finite presentation of a module M is a sequence, is an exact sequence. R to the M R to the N to M. So is this, let's say, a sequence exact at, well, I guess so let's make it an exact sequence. Is an exact sequence. So we saw lots of exact sequences in algebraic topology, right? So this is an example of an exact sequence. So this is surjective. So making this exact means that it's exact here and here. So this is surjective, and then this map is not necessarily injective, right? And so a module M over a ring R is finitely presented if it comes with a finite presentation.
Is that necessarily finitely generated then also, or?
Yeah, finitely presented implies finitely. So finitely presented implies finitely generated. So because there's this surjective map. Okay, so note. So what do we have? So note. Okay, so let's go back over here. So now we've kind of gone here. well, I guess we can still go this way. So note that, yeah, you're right. So note finitely presented implies finitely generated. Okay. Let me just say something abusively. Let me just say something else here abusively. Or abusively, if there exists a finite presentation, but we don't specify it. We will always we will call the module finitely presented. Okay, so let me kind of make for the computer algebra people, let me make an important distinction here. Okay, so in a computer, right, you can only specify modules by finite presentations, right? And so you don't just have a module, but you have this matrix also that encodes the module. And so you need to work with the category of finite presentations, which is like these matrices, in order to do anything in computer algebra. A lot of the time, we just assume that it's finitely presented. Like when we're doing theoretical work, we assume that it's finitely presented, and in the sense that there exists something like this, but we don't we just deal with them as morphisms of modules, not morphisms of finitely presented modules, right? Yeah. Okay, so yeah, so here is my note. So finitely presented implies finitely generated, and finitely generated in Noetherian implies finitely presented. Okay, and so here's why I had to make that comment, right? So finitely generated in Noetherian, I said it's finitely generated, but I didn't give you the generators. If I give you the generators, right, in some way, I don't know how you would really give me the generators without giving me a presentation. But if I give you the generators, I mean, there are ways to give you generators. If I give you the generators, then you can look at the kernel, right, and then you can start to build the presentation. But just because it's finitely generated doesn't mean I've handed you the module with the generators. It's like the difference between handing you a vector space with a basis and handing you a vector space and knowing that a basis exists, right? That's kind of the distinction that I'm making. And so, yeah.
Is the Noetherian required because you need that for the kernel to be finitely generated?
Exactly. Or, and so if you have a map and you know that the kernel is finitely generated, then you get finitely presented as well, right? But yeah, that's what we need. We need this for the kernel to be finitely presented. There's another way. So like as an aside, okay, as an aside, there is the kernel of the kernel, right? We could keep going. If we wanted to. And so then you have like M0, this goes to R, and let's just use letters now, R to the N2. And now, in this one, you have like the kernel of the kernel, right? So this one would be the kernel of the kernel. This is called the syzygies. Oh man, syzygy. This is the syzygy relations. So this is the relations among relations. Okay, and if I were going to keep going like this whole thing here, so this is like A1, this is like A2, but you get a bunch of matrices like this. Okay, and then this whole thing is called a free resolution. of M. Okay, so like if I take a sequence like this, so the sequence, I guess, depends on the generators that you pick at first. But once you keep going like this, you get what's called a free resolution of M. And we use these. Okay, so this is an exact sequence. Okay, and so we use free resolutions. And maybe we'll do this at the end of class if we have time. I don't know. We use this. We use these to build functors, build derived functors. Like Ext and Tor. Okay, so maybe later. Now we know what a free resolution is, but this is one way to get free resolutions, and maybe we'll do this. But the idea is that you have an exact sequence here, and one of the things that you do is you'll apply a functor to this exact sequence, right? And the functor will not be exact. So what'll happen is that this thing, which is an exact sequence, turns into a chain complex, right? Instead of an exact sequence. So instead of the image being equal to the kernel, the image will be contained in the kernel because the functor isn't exact. And the homology of that sequence are the higher derived the derived functors. So I guess I can say that yeah. So what you do is you apply a functor, an additive functor. Okay, so that just means that it needs to map to another abelian category. Okay, so that's not exact. Our free resolution turns into a chain complex. And then you take the homology of the chain complex. And that gives you, so this thing, these are the derived functors. And it turns out, magically, that this whole procedure is independent of the resolution that you pick, right? So it's independent of this sort of resolution.
Is there a reason for the name derived? I've heard that.
Yeah, well, it's derived because like I had to do this crazy thing to make it, right? Like it's like it's not an obvious functor. It's not like HOM or like some other like a fiber product or something weird. I had to do this really weird thing where like I built this free resolution, then I applied a functor to it, and then I took homology. That's kind of a convoluted process, right? And so it's kind of derived. I derived it. That's the idea, I think. Yeah. Okay. So all right. All right. So let me get to the kind of the punchline here. So we did finite presentations. So let's do finite presentations of, okay, so the main point again. So again, the main takeaway. We can get matrices A so that, modules M is isomorphic to R to the N modulo the image of A. Okay, and A also encodes the kernel. Yeah, but this is kind of like the main point here. Okay. So for finite presentations of modules over PIDs, there's something special. Okay, so PIDs are special, right? They're like kind of like extra Noetherian, right? They're like more than Noetherian. They're it's a much stronger condition than Noetherian. Okay, and so for modules over PIDs, for PIDs, every submodule of a free module is free. Okay, this is a big important fact. Okay, this is not true in general. So like, let me give you an example. If M is just R to the 1, right, then this is just saying that a submodule of, in R to the 1, let's take a submodule, let's do it like this. What's a submodule of R to the 1? A submodule of R to the 1, so R1, a submodule here. This is what a submodule here. And so by this being a PID, this looks like A times R for some A in R, right? It's a principal. Okay. A non-example, right? R, if we take R to be C of XY, this is not a PID, as demonstrated by the ideal generated by X and Y. It's not a principal ideal. It's not generated. This is not a free module. And remember, we said before that this thing here was isomorphic to R, right? So the submodule of the free module is free. This one here, this is not isomorphic to C of XY. There's relations between X and Y. So the idea is like free is like no relations. Okay, so now let me tell you the theorem here. Theorem.
On that last example, it's not the ideal. It's certainly not shows it's not a PID. It's not a free module.
Yeah, this is not a free module, right? This is not a free module.
It's not generated by.
Well, it is generated. It's finitely generated. It's generated by two things. But notice that if M1 is X and M2 is Y, right? Then we have the relation Y M1 minus X M2 is equal to 0, right? So this is a relation among the two generators.
And therefore not free. Okay.
It's therefore not free.
Relations, yeah.
Relations means that it's not free. Okay, that's what it means to be not free. Okay, so theorem, this all comes down, the modules over PID theorem comes down to the Smith normal form. And so what we're going to do is we take the matrix that comes with the presentation and we put it into a very special form so that we can compute the image. Okay, so if R is a PID and A is a matrix like the matrix we're interested in, so this is an n by m matrix, there exists some invertible matrix P in the set of invertible matrices and some Q in the set of invertible matrices on the other side, such that, okay, and so these P's and Q's are essentially obtained by row and column operations. Not essentially, they are, right? Such that PAQ is equal to S. This matrix S is what's called the Smith normal form. It's essentially the reduced row echelon form, but for it's the it's the reduced, it's like a row echelon form, but since we're not allowed to divide in our ring, we have to be a little bit more careful, right? And so this thing looks like A1, A2, ... up to AR. So there's zeros here, zeros, and then this goes on 0, 0. It's a big diagonal piece, and then it's zeros everywhere else. Okay, so there's this diagonal block, and the important part about this is that A1 divides A2 divides A3 divides dot 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 divides AR. Okay, so the matrix S is unique. It is unique up to, let's say, associates of the AIs. And we also call the AIs the invariant factors. Terminology. So we call these AIs in here, the appearing as the diagonal elements, invariant factors of the matrix. Okay. So this is where our invariant factors come from. So what we did is we get a presentation. The presentation essentially boils down to this matrix A. A tells you, you know, what essentially the relations among the generators are. Okay. And this thing. So let's now we can prove. So using this. So using the Smith normal form. Okay. So now we can give a proof of the fundamental theorem. Using that Smith normal forms exist. SNFs. Okay, so what we do is, okay, so we have this thing. So we have R to the M. We had our matrix A, and we have R to the N. M. And we have some F here, right? And okay, and so what we'll do is we change basis here, P R to the M. Maybe I need a Q or Q inverse here, R to the N. So let's see. So maybe one of these needs to be inverse, but let's see which one needs to be inverted. Again, then we have this map here. This is FQ inverse. So let's see. So we had, this is S, and S, what did we have? We had S was equal to PAQ, is that right? Or QAP? PAQ, I think. So so S was equal to, so you do P. Oh, so you do P, so this should be P inverse. So PAQ. So the P inverse AQ. Yeah, okay, so yeah, so this is P, this is Q here. Okay, so we have this situation here where we have the Smith normal form. Okay, so this is still exact, right? This sequence is still exact here. This is still exact. Still exact. So that means that M is isomorphic to R to the N modulo the image of S. Okay, and let's figure out what the image of S is, right? So the image of S. So if we use this form here, so the image of S looks like this crap, the stuff on the diagonal, right? So this looks like A1 R, direct sum A2 of R, direct sum dot dot dot, direct sum AR of R. Okay, so this means that if we take this quotient, R to the N modulo the image of S, so we essentially have R to the N modulo A1 of R direct sum, A2 of R direct sum, AR of R. So this thing here is really isomorphic to R mod A1 of R, direct sum R mod A2 of R, direct sum blah, 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 direct sum R mod AR of R. So these are these submodules. And then we have everything, we have this free part of this rank. Okay? So this proves the result. Okay, and that's the end of the class today. Okay, so I'll stick around and answer questions. I'm going to stop the video, but let me just give you the exercise for the day, or the quiz problem. Okay, so the quiz problem is state and prove the Chinese remainder theorem. All right. I'm going to turn the video off and then address some questions if you guys have any. Or the recording off, I mean.